Okay, yeah, sorry for the mess up. Somehow the file was not, I didn't copy the correct file, so I have to do it again. Okay, so we continue our topic about voting and social choice. First, what's going on? Okay, so first the outline of the topics. So we are going to see several more examples of voting systems or social choice functions for the election with 3 or more candidates. Okay, so these names will make sense in a moment. Okay, and then in the second half, we'll prove a very, very famous theorem called Arrow's impossibility theorem. Arrow is a name, is Kenneth Arrow, a famous economist. Okay, so so let me begin with answering a query. And at the same time, this will refresh our memory. So we'll see where we stopped last time. Okay, so last time I defined a social choice function or a voting method. So it is a function with domain, the set of all possible profiles. So imagine that everybody voted. So I collect all their votes here. So now the voting method or the social choice function is going to give us some output based on these votes, right? So the output I define is this. So the codomain is the non-empty sets of possible orderings of the candidates. So remember here we have more than 3 or more candidates. So the vote is not a single name. So usually each voter has to provide an order, right? A list of names in a particular order. So the most preferred guy is appear on the top, and the least preferred guy is appear on the bottom, right? So the input is the set of all the votes I collect, all these ballots I collect, right? And then the output will be, I'll give you some of the choices. So I'll get the most popular choice or the best choice based on these votes, right? So this is what I define. So the output is not a single name, but it is also a list of preferred ordering, right? So this is what I did last time. And okay, so let's make a small summary. So in other words, a social choice function tells us the society's preferred choices, right? So okay, so then in a few slides later, I said this. So the popularity method, right? So in particular, we have one method. It's like the simple majority, but here we have more candidates, so we call it popularity method. So it's a social choice function that selects the winner, select as the winner the candidates who are ranked as the first choice by the most number of voters, right? So I look at the top choice of people. If Mr. A gets the most, I mean, the first choice for most of the voters, then Mr. A is the winner, right? So I said this, right? Now, the sharp reader, one of you, make this query. Is quite nice. So he asked, the plurality method I just said only produce a winner, right? So I did say, okay, it just select the winner, right? It is the the method does not produce an ordering of the list, does not produce a list, only produce the top guy, one guy, or possibly there's a tie and then there's a few guys, but not a list. So is this a social choice function, right? So I said here is a social choice function, but literally these two items are not, how to say, doesn't fit, right? So what's going on? Okay, so indeed I missed something. So the answer is actually these two, I'll call one winning producing function, right? So the plurality method only produce winners, right? So this literally is not a social choice function, but it can induce. So from this we can get a social choice function. Well, the way it induces is quite easy, because suppose you get Mr. A as winner, and then we can remove A from the ballot, and then the social choice function will have domain of all possible profiles. So let's assume if you have a way to choose candidate for 5 people, then you have a way to choose candidate for 4 people, 3 people, 2 people. So it's a systematic. There's a family of method, right? So if you remove the winner, and then you can use the same method, like the plurality, or to select the runner-up, and that will be your second choice. And then you remove it again, and then do it, calculate, and then you get your third choice, and so on. So you indeed, any method can produce a top person, can rank person, can produce the list, right? So this is okay. On the other hand, if you have a list, then certainly you can produce the top guy, because suppose you have one list, then you just take the first guy, the guy who is on the top, right? So although literally the social choice function and the winner producing function are not the same, but they are not far away. So for this course, we don't distinguish them, right? So that allow me to be a little bit sloppy, so that we can assume the social choice function produce a winner. So it's no big deal. Okay. But indeed, if you spot these kind of questions, do alert me, because it's literally the previous slide had some problem, so it needs to fix. Okay, so, but you can fix it in this way. Okay, so hopefully you are happy with this. Okay, so now, now we know what is the plurality method, right? So now let's make some remarks on this plurality method, voting. So it has some very nice properties. It also has some drawbacks, right? So the nice properties, okay. So when we talk about election with 2 candidates, we have defined this anonymity, neutrality, and monotonicity, right? So this anonymity says the voters are treated equally. It's not one person vote counts a lot more than others, right? Everybody are treated equally. And this neutrality means all the candidates are treated equally. There's no favor for particular one, right? This monotonicity says, suppose A is a winner. If you move some losers' vote to A, and then A is still a winner. So, right, so the winner gets more vote, doesn't hurt. So this is the monotonicity. Okay. So the plurality voting satisfies these. You can check. It's quite easy to see. Okay. So plurality satisfies all of the properties. Okay. So it's nice to have. But there's a problem. So with 3 or more candidates, there are all sort of strange things comes out. Okay, so the one of the problem is this, the Condorcet. So remember that we defined something like a Condorcet winner. So Mr. A is Condorcet winner if he compete with any other person, he will win. Suppose it's a two, so if we pit Mr. A with somebody else head to head, then Mr. A always win. So he wins every single, how to say, one-to-one game. So that Mr. A will call the Condorcet winner, right? So the problem for the plurality voting is a Condorcet winner may not be the ultimate winner, right? Although you are better than any single person, in this voting system, you may not be the winner. So this is slightly not so nice, right? So anyway, so this is a concern, right? Now there are some other concerns, like so the winner may receive less than 50% of the vote because it's possible that the vote somehow split among several persons. So this guy just barely win the other. I mean, barely get more, maybe just one vote than other people, right? So he is still declared as a winner, but he didn't receive half of the vote. That's possible. And also, somehow there are some other concerns, like maybe a large portion, a sizable portion of the voters gets no representatives. So that there are some concerns for plurality vote. We are going to see probably one or two more concerns, or either in the notes or in the tutorial. Okay, so that's the sort of the brief review of what's happening on Tuesday. So if plurality have some problem, how about other method? So in this lecture, we are going to introduce three different methods. And along the way, we introduce some other criterions, other properties. Okay, so the first one is called border count. So this is based on a person, right, called border. So this the method he suggests goes like this. So we have this profile, right? So we give 1 point to the first person, 2 points for the second person, 3 points for the third person, and so on. So each person, depending on the position he appear on the ballot, he'll receive certain points, right? And then we add up all these scores, okay? So we add up the scores of each candidate for all votes cast, right? The one with the lowest total score wins. You see we put 1 point for the first preference. So the smaller the number is, the better, right? So this is the plan. This is the method suggested by border. Okay, so you can change this. Say you can give. Suppose you have n candidates, you can give n points to the first one, n minus 1 to the second one, and then you select the guy with the most point, right? It's the same. So we stick with these two are equivalent, obviously. So we forget about this. We give 1 point to the first person, 2 points for the second person. We do that. Okay. So there are applications, real life applications for this method. So there are, I don't know. So there are Slovenia, Iceland, and also this Major League Football's MVP, most valued players, are selected by this method. Okay. So there are some values. Okay, so let's look at some examples. So example of border count. So suppose we have 4 candidates, A, B, C, D, and so there are 2 votes goes for this order, C, A, B, D. 2 votes for this order, and 1 each for the other. Okay, so we do the border we calculate the score. So let me just calculate A, then you know what's going on, right? So you give the rank 1 1 point. Okay, so A gets 1 point here. So this, right, there's one person put A as the first choice, so A get 1 point. Now, how many person put A as the second choice? So here you have 2, right? First column provide 2. Second column also provide 2. So there are 4 person choose A as the second preferred person, right? So you get 4 times 2, that's 8, right? So we get 9 for the first 2 rows. Now, for the rank 3, you get 2 occurrence here, each one, okay, so you get 1 and another one put A as the third choice. So you have 3 plus 3, right, points for A. So that's 6 points. So just now we have 9 and 6, so we get 15. The last one has no A, so there's no, right? I hope you can help me check whether these calculations are right or not. Okay, so you do the calculation for each person, and then you add them, add the score. Remember the person who get lowest score is the winner. So A is a winner in this situation. Okay, so it's quite simple. Okay, so now is this the ideal or the best? So the problem is border count. Well, there are probably several problems. So well, somehow we look at this. We look at this profile. So you can check that the border count totals for A, B, C, D, E are these numbers. Okay. If some of you have a calculator and nothing to do help me check this, right? Okay, so according to the rule that the person who gets lowest score wins. So in this case, B gets lowest score, right? So B, Mr. B wins based on this border count. Okay. Now, however, if you look at this, there are 70% voter prefer A to B. Why? Because so there are 3 person here prefer A to B, 4 person, so there are 7 person already, another 4. So this is 11 person, and then another 4, 15, right? Now there are 5 people prefer B to A, but 15 people prefer A to B. So actually 70% voter prefer A to B, and another 25% prefer B to A, right? So this border count somehow, in this particular example, didn't reflect this. Whether this is a good thing or bad thing, we can debate, but the fact is this. Okay. Okay, now there's another problem, and this problem will lead to another criterion, to another property. Okay, so let's look at a simpler problem. So here, suppose you have 3 voters choose A, B, C in this way, and 2 voters choose C, B, A in that way. Okay. So now again, we have to try the border count. So let's see C, right? I don't trust my calculation. So C, so 2 person rank it number 1, so he has 2 points here. Then 3 person rank him number 3, so you have 9 points here, so it's 11, right? So something like this, right? So now if you count this, 9 is the lowest, so the winner is A. Okay, so clear. Now here, imagine another scenario. Suppose 2 voters in the last column, somehow the 2 voters here change their vote to, instead of have CB, they have BC. They swap their preference of B and C. it didn't change A. A is remain there, and they only change B and C. Okay. So now if you do this change, the B somehow the points for B become smaller, right? So the A is still 9. Nobody changes preference, but B become 8 because in the past you have 4 points comes to here, another 6 point come to here. But if you change the preference, you get 2 points from the last column, so you get only 8. So B is a winner, right? Now, is this a problem? So why should A? Okay, so A is not happy. Why? So can he give some reason? So why he is not happy? So here this brings us a property called independence of irrelevant alternatives. Okay, so the above example shows that the border count can violate the so-called this independence of irrelevant alternatives. Okay, so because it's too long, there's a shorthand for IIA, right? So I call it IIA. Okay. So what is this irrelevant alternative? So if A is a winner of an election, then it is not possible for B become a winner without some voter change their order of preference from B less than A to B bigger than A. You see, they think that if you compare A and B, only relevant thing is the ranking between A and B. All the other flippings are irrelevant, right? So this is the relevant. So if you don't change the relevant things, you only change the irrelevant things. You shouldn't change the result, right? So put it in another way, if the system rank A above B in the presence of C, then it should rank A above B when C is not there, because C is irrelevant, right? So so we would like our voting system to be insensitive to the presence of such irrelevant alternatives. Okay, so first, do you understand what the rule says? Right? The rule says, suppose in the voting scheme give you the social choice function, give you A above B. Now, if you don't change any vote, the order of A and B, you change some B and C or C and D, and it shouldn't change the result. So A will still be above B. So this is the independence of irrelevant alternatives. Okay. So so we understand this, right? So whether this is a reasonable condition, well, again, we can talk, right? So actually, this IIA is I think is introduced by Kenneth Arrow, and he used this. So you'll see that in his impossibility theorem, this IIA play an extremely important role. So so I think we can see there's a point, right? So there's a point for him to introduce this IIA, but this is not as natural as other criterions. Okay. All right. Okay. So the plurality is not IIA. For example, consider this example. Okay. So there are some numbers. Okay. So A gets some vote, and so this is a profile. Okay. Now using the plurality method, we get, okay, how many choose A as the first one? 49, right? 49. How many choose B? 47. How many choose, how many choose C? 47. How many choose B? 4. Okay, so A is a winner. This is by plurality. Okay, now let's do some irrelevant alternative. So we flip this B and C, right? So if the voter who rank candidate B first instead of, okay, suppose you flip this, right, B and C, so you get 4 more first choice for C, right? So then it becomes 51, right? So C will be the winner, right? But this flip of B and C doesn't change A, right? So it shouldn't affect whether A wins or not. We only change B and C. So this is irrelevant alternative, but somehow it can change the result. So plurality fails, the so-called IIA. Okay, so now, so that's border count and some problem, and we introduce IIA. Okay, so now we introduce another one. So we just see some examples, and then we study what is the good thing about this, what is bad thing about this. Okay, so here's the second one we are introducing today. So it's called the sequential pairwise voting. Again, too long, so let's call it SPV. Okay, so first the motivation. So the motivation is this probably is inspired by the sports, right? So you imagine, so in sports we have the tournament, so the team will play in the tournament, and then so he'll stay in the tournament as long as he wins, and the first game he loses, then he's out, right? So this is the thing happens in lots of tournaments. Suppose you don't have this round ribbon group stage. You just do this. Just if you lose one game, you're out. Right? Okay. So the team that wins the final contest is the tournament winner. Right. This is what's happening in some sports. So now we want to use this idea in the voting, in the social choice function. So in the voting theory, so first we make a schedule. The schedule of head-to-head matchups is called the agenda. Right? You can imagine, as in sports, the order is important. Maybe some team, I mean, just how to say, some team will be very bad against some other team, but he can win other guys, right? So sometimes, if you are unlucky, the first round you hit your enemy. I mean, the one always win. Then against you, then you are out, right? So sometimes it's like that. Anyway, so in voting theory, we also have agenda, which is the order of the competition. So usually it's a sequential order. It's a sequence, right? It's sequential order, and the matchup will follow the order of the list. You have a list of candidates, and then the order will follow the order of the list. So that's why it is called a sequential pairwise voting, right? Okay, so or some people call it agenda method, but we follow the name SPV. Okay, so let's look at, so the previous slide is for the inspiration, where the idea comes from. Now, this is more specific about the idea. So suppose we have a number of candidates, A, B, C, D, etc. So we list it in this way, A, B, C, D. So the tournament or the voting will play A against B, right? So we first pit A against B and ask who the voter prefer. Okay, using some like the majority or simple majority method. Okay, so then there's a winner. So the winner will come against C, right? And then it produces another, possibly some other winner, and the winner will play against D, and so on, right? So in the end, who survived the last game is the winner of the whole tournament or the voting, right? Okay, so the winner is the last one still standing. So by the way, so the remark is if there's a Condorcet winner, then she will be certainly a winner under this SPV. right? By definition of Condorcet, the winner is going to win every head-to-head game, head-to-head vote. So if she is the Condorcet winner, guaranteed she is going to win. Okay. Okay, so let's look at some example of this this SPV. Okay, so we have a number of votes. Suppose we have this, right? Okay, I will not read these. Now we have to fix an agenda. So we have to have a sequential list, right? Suppose the agenda is A, B, C, D. Then let's see what happens. Who is the winner? So A beats B. Is it true? So here you have people vote A above B, A above B, A above B. Okay, only one vote put B above A. So A against B, A is going to win, right? So the winner is A. And then so the winner will play against C, right? So A and C, who is going to win? So you have 2 votes for C above A, then A is above C. Okay, 3 votes C above A, A above C, A above C. So there are 3 votes for C above A, but A above C is 2 plus 1 plus 1. So there are 4 votes. So A wins against C. Okay, so A wins against A will beat C. So now A is going to play against D. Who is going to win? Okay, 2 votes A above D. Okay, so 3 votes, 4 votes. So there are 4 votes. And then the other 3 goes to D above A. So again, A, is it? A, okay, so let's try again. So A above D, 2 votes. No. A above, 3 votes, sorry. I was wrong. So 3 votes for A above D. Now, how many votes for D above A? So 2 plus 1 plus 1, so 4, right? So D beats A. So if we choose the order like A, B, C, D, then D is the winner, okay? Now, suppose we choose a different sequence. So we choose B, D, C, A. Okay, so then in this case, let's see what's going on. So B is going to play with D first, right? So B is, okay, according to this, B beats D. Is it true? So 2 votes for B above D, and another 1 vote, so there are 4 votes at least. So 4 is majority. There are only 7 votes, right? So B beats D. And then B is going to play against C. So the picture says C beats B. Is it true? Okay, 2 votes. So there are at least 4 votes. So C definitely beat B, right? C beat B. Now, so C is winner. Then C is going to play against A, right? So okay, A beats C. Is it true? 2 votes C above A. Another 1 vote. So that's 3 votes, right? So again, it's 4 against 3. So A is a winner. Okay. So actually, this shows the SPV is not. It's just like sports. Sometimes it depends on your luck, right? So if the order is right, you win. If the order is not in your favor, then unfortunately you're out, right? So it's a little bit random. It's not really robust. Okay, so now there are probably other problems of SPV. So here's another example. So suppose we have a list like this. Okay, I will read it in a moment. Okay, so suppose we have the agenda is A, B, C, D. Okay, so it's A. Okay, so then so then A beats B. I don't know. Is it true? A is above B. A is above B. So there are 2 votes against 1 vote. So A beats B. So then A is going to play against C. So A is play against C. So A beats C. Okay, C beats A, right? Is it? right? C beats A, because there are 2 votes for C above A, only 1 vote for A above C. Okay, so C beats A. So then C is going to fight with D. Okay, C is going to fight with D, while D beat C by 2 against 1, right? So D is a winner, right? So according to this agenda, SPV, D is going to win. Now the claim is, this is extremely unfair for B. You see, B beats D in every vote, right? So now by playing this SPV, although B above D in everyone's ballot, and in the end, B loses. So this is not good, right? So it's like a favorite team somehow because of the something happens, then because of the luck, right? He was eliminated earlier by some underdog, and then okay. Anyway, so this brings us another condition, right? So we are clear about this, right? So for SPV, it could happen that hot favorite, right? So Mr. B somehow loses the election. Okay, so now we want to describe this phenomena and try to add it as a condition. So the condition is Pareto. Okay, so this guy somehow he's an economist. I think if you study economy, he was quite famous. He's an important guy in some part of economy. Okay, so we introduce a condition or criterion called Pareto. Okay, so the above example shows that SPV can violate the following condition. It will be called Pareto condition. Okay, if every voter ranks B above D, then the system should rank B over D. Right? If every voter rank B over D, then D should have no chance. D should be eliminated the first round. Okay. So in particular, if every voter prefer B over D, then D should not be the winner of the election. Right? So this is called Pareto. Okay. So this is called a Pareto or unanimity condition. Okay. Right. Unanimity means everybody rank B above D, and then D should be eliminated. Okay. I think do you agree that this is a reasonable condition? It's all subjective. So some conditions looks more reasonable than others, but this seems to be reasonable, right? Okay. So let's look at some examples of Pareto. It turns out this dictatorship is a satisfied Pareto condition. I'll remind you the dictatorship. So dictatorship is, there's one guy called dictator, and we just look at his ballot. If he ranks somebody on top, then if he ranks Mr. A on top, then Mr. A is a winner. No matter what other people do, there's no chance. So that's the dictatorship. So we claim that dictatorship will satisfy this Pareto condition. Okay? The reason is quite simple, right? Because you see the Pareto condition requires everybody rank Mr. A above Mr. D, right? So in particular, let's say, so if candidate X is ranked above candidate Y in every profile, in every ballot, I should say, and then in particular, it is true in the dictator's ballot, right? Because it's everybody, right? So therefore, Y cannot be dictator's first choice, so Y cannot win, right? So the dictatorship, a very bad method, somehow on this aspect is good. Okay. On the other hand, this monarchy are not Pareto because the monarchy it doesn't depend on the voting, right? So no matter how you rank person, no matter how, even if everybody prefer X and Y, then Y could be the monarch. So Y still wins, right? So this method does not satisfy Pareto. Okay, so so far so good. Okay. One last method for today. Actually, there's another 5 or 6, and we can talk about many others. But so I think this is the last. Okay, so it's called Hare's system. Again, it's proposed by a British politician, Sir Thomas Hare. It's around in the 19th century. Okay, so the proposal is this. So we examine the voter's first choice, first preference, and eliminate the candidates who have the lowest number of first positions. So if you are the last preferred, you are out. And then let's look at it. So after we remove the person, we look at the remaining picture. Okay. So having eliminated these, we examine the new preference list and repeat the same procedure. It will become clear when we have an example. So basically is we look at the profile, we eliminate the least preferred person. And then we look at the remaining situation, we choose the least one, remove them, remove him or her, and then continue, right? Okay, so the winner is the last one who remains. So it is possible to have a tie, but let's make our life easier. Don't discuss. Let's not discuss the tie situation. Okay, so here's the example. So suppose you have the profile like this, right? So we want to see what happens under this Hare system. So now, so we have A, B, C, D. So we look at the first choice. Okay, so C has 3 first choices, 3 votes. D has 2, and A and B both have 1. So the least preferred are A and B, right? Because they only get 1 vote each. So they tied at the least preferred position. So they are out. Okay? So A and B receive only 1 first place vote, whereas C and D have 3 and 2 respectively. So A and B are eliminated after round 1. Okay? Now, after you remove A and B, for example, you look at this column, if you remove B, D will become the first choice. Okay, so that's the important observation. Okay, so with only C and D left, C now has 3 first choice, and D has 4, right? Because the first choice C and D remains here. If you remove B, you increase this. Okay, you increase the count of D by 1 vote because B is out, no more. Look at the last column. A and B both are out, so D become first choice of the last one, right? So is this one A and B are removed, C has 3, but D has 4. Okay, so in this case, D is a winner. Is this all right? Okay, there are some remarks. So first, suppose you have many candidates, you would think that this requires many rounds. It's a very not so effective, right? But it turns out with the help of computer, it's very easy to handle this. So practically, this is feasible. It's not too bad. It's not like we have to cancel the A and B. So the computer can do this in 1 second. Okay, so this is one remark. The other remark is more important. So the form of runoff election assumes that the voter hold consistent preference once the candidates are removed. You see, usually when you remove candidates, you ask people to vote again. But people would change their mind because possibly, right, because of the, suppose originally B and C are similar, and if you remove C, then the people will vote for B, right? So in many situations, if you remove some candidates, the people can change their mind, can get a different order. But in this higher system, you are not allowed to change your mind. So we assume that you only vote once, and then that determines the outcome. It's not like you vote the first round, after you remove somebody, you vote for second round. So that's another method. But higher system is not that. Okay, so now there are some, so practically some people use it. So Australian House of Representatives, and in India, and somehow is elect president and parliament. Okay, so it was used in real life. Okay. All right, so then, as usual, we'll look at the problems. And okay, so the problem with hair is, okay, so look at this profile. So since B and C have 4 first place votes, whereas A has 5, is it true? B has 4, C has 4, right? So A has 5. Okay. So therefore, we'll eliminate B and C, so A is a winner. Okay. Now let's do this irrelevant alternatives. Okay, suppose now the voter in the last column switch. No, it's not the irrelevant. Sorry, so this is another. So now suppose the last voter swap the position B and A. So he upgrade A to the first choice. Then you would think this move is good for A, because originally A was ranked second. Now he's even ranked number 1. So you think this will help him. But no. But if you do this, what do they have? So you have this situation, because the last one become ABC. So it is the same as the first 5, right? If you swap this, you get ABC. So it's the same as the first 5, so you get 6 votes for ABC. Now if you do this, so B is out in the first round. But however, after B is out, this C suddenly get 3 more first choices. So C will get 7, right? So C beats A in the second round. So this method will produce C as the winner in this situation. Okay, so this violates the monotonicity. So I guess I don't need to repeat the monotonicity, right? The monotonicity says if A was a winner and you are trying to help A, right, by give A more votes, and A is still the winner. You shouldn't hurt A. But in the higher system, this example just showed we are trying to help A by giving him 1 more first choice. And it turns out A get out, right? So this higher system violates this monotonicity, right? So this is so we have seen this in a two candidates voting system, right? So higher system violate this. Okay. Okay. So now we have seen 3 more voting system, right? Now three of them they all. Okay. So we have seen 3 more. On Tuesday we saw this plurality, right? So we have seen 4. Okay. And also we have seen dictatorship and so on and so forth, right? But these four are probably is actually used. Okay, so each of them seem reasonable, but may violate some of the so-called desirable properties. So sometimes it's Condorcet, sometimes it is IIA, sometimes it's Pareto, sometimes it's monotonicity, right? So now the question is, again, right, is there a best system? So is there a voting system which is, okay, so these are the properties we prefer, right? Anonymous, neutral, and decisive, right? Always produce a winner. We encounter this in a two-person election, and satisfy the four properties: Condorcet, IIA, Pareto, monotone. Right. So is there a best system? Is there an ideal system? Okay. So is the question clear? Okay. Now the answer turns out to be no. So now this Kenneth Arrow, he won a Nobel Prize in economy. So the discovery of this impossibility theorem was one of the main reasons that he was awarded the Nobel Prize in economics. Okay, so here's the theorem. The theorem by Arrow in 1950. So 1950 is a very exciting year, right? Nash also published his paper, and Arrow had his result also on 1950. So with three or more candidates, the only voting system satisfying Pareto, IIA, monotone, and decisive is dictatorship. Well, dictatorship, why this is an impossibility? So dictatorship will violate, for example, anonymous, right? I mean, dictatorship is bad. It's not the ideal system. So now if you don't even need to consider Condorcet or something else, right? You just consider Pareto, IIA, monotone, and decisive. Then there's the only choice is dictatorship. If you add anonymous, impossible. There's no such voting system which can get these four plus, for example, the anonymous. Okay, so this is result by Arrow. Okay, so let's take a break. In the second half, we are going to prove it. Okay. Anyway, so let's take a break. Okay, so let's continue. So the remaining of this lecture is going to devote it to the proof of Arrow's theorem. Okay, so let me say this is optional because this is not a mathematical course. But on the other hand, why do I want to show the proof? Because we can, right? Because this is a sort of like Nobel Prize winning results, right? And somehow it's simple enough for us to understand. So it's long-winded. It take maybe half an hour. But still, every step I hope, is simple enough. I will convince you that this is true. Okay? So let's do it. Okay. So what is the statement? What do we want to show? So suppose we have a social choice function f, because I'm going to refer to this function many times. So let's give it a name. Let's call it f. Okay? So let's call this function f, which satisfies the Pareto, IIA, monotonicity, and decisiveness. Okay, so it has the four properties we want to have. Now we must produce a dictator, right? So the Arrow theorem says if the voting system and social choice function are the same. Okay, so if the social choice function satisfies 1, 2, 3, 4, it must be dictatorship, right? So we are going to show you this is true. So give me an f which satisfies 1, 2, 3, 4. I want to convince you that there is a dictator. So his vote, only his vote matters. Okay? So this is the plan. So it's hard, right? How can I, just from the information, it satisfies 1, 2, 3, 4, where can I find the dictator? Where is he, right? I don't have any information of the voters. How can I find the dictator? Okay. Okay, so now that's an interesting part, right? So to prepare the proof, we need to introduce some definitions and make some observations, and then we cut the proof into 5 small lemmas. Lemma is a mathematical jargon for facts or for single proof, right? Okay, so you can think of this as 5 steps. Okay, so I'm going to show the big theorem in 5 small steps. It sounds bad, but actually it's good because each step is easier to understand. So okay, so be patient, right? So it has several things, but this is a big theorem, right? It's a famous theorem, interesting, so it's worth it. Okay. So the first definition I want to introduce is this. So suppose X is a set of voters. Just you have lots of voters. So for example, in Singapore election, right? Every Singaporean is a voter. So X will be a subset of the voters, like people in this LT. Okay, so let X be a set of voters, not to be the full set, just some subset of voters, and A and B are 2 distinct candidates. So A and B are candidates; they are different. It's not AA, right? So it's A and different person is B. Okay, so we say that X can force A over B. So I'm going to define this phrase, this sentence, the meaning of this. X can force A over B. If F prefers A over B, whenever everybody in X plays A over B in their ballot. Right? Suppose everybody in this room prefer Mr. A, then the whole Singapore will prefer A. So in that case, this X can force A over B. Is it clear? So let me try again. So whenever everybody inside X plays A over B, then F, the system we are talking about, will go with X. We'll say A is over B. right? So this is the definition. Okay, now this is then we make an observation. So the observation is long, but this is crucial in our proof. Okay, so the observation says this: in order to show X forces A over B, it suffices, we only need to show, to produce a single preference profile with the following properties. Okay. First, everybody in X has A over B in their ballot. 2, everyone else will have B over A in their ballot. Okay? And in this situation, F go with us, with the X. F prefers A over B. So suppose we have one situation that F goes with X, then we can conclude X force A over B. Is the statement clear? The statement says, okay, now I want to show that X force A over B, right? So whenever the group, the people in X vote A over B, F must go. So I want to say, I don't need to check all possibilities. I check one possibility. If in this situation, if everybody has, in X, has A over B, everyone else are against having B over A. Now, if in this case, F goes with X, and then X force A over B, right? So is a statement clear? It's a bit long, but okay. Let me make the last attempt. Okay. So you see the definition says whenever, right? Whenever X in A, everyone in X plays A over B, and then F will go for A over B. So the whenever actually include lots of cases, right? So the observation says the whenever can be reduced. I only need to look at one particular case. That particular case will determine every other cases. The particular case is everyone in X prefer A over B, and everybody else is against X, prefer B over A. Now in this case, F still prefer A over B. So in this, if there is this situation, 1, 2, 3 happens, then we achieve this whenever. Okay, so right, so this is the observation. What's the reason? So what are the other cases? So what are the whenever? What is 1, 2, 3 missing? Right. So he missed two things. So the other cases are because he didn't mention, you only see A and B. It didn't mention C, D, and E, right? So how people in group X put C above A or put C less than A, so it didn't mention this, right? But it doesn't matter, right? So this is because of this IIA. What you do about C and D is irrelevant. We only care about A and B. So we don't need to consider C and C, D, E, and so on and so forth. So therefore, we only need to consider this. The other situation is, okay, here he assumed 2 holes. So everyone not in X are against us. For 1 has no choice, because to verify its forces, everybody in X has to put A over B. So we cannot, we don't have any freedom for 1. We don't have any freedom for 3. But for 2, you may have, maybe we have somebody else sympathize. And maybe outside X, there are people who put A over B. But if 1, 2, 3 holds, by monotonicity, there are people who change their mind to help A, well, by monotonicity, things are better. So we still have, F will still have A over B, right? So, well, so that's the reason, right? So here we use IIA, we use monotonicity. So we reduce the checking of X force A or B by checking 1, 2, 3. And this will be used later. Probably at that time, I'll remind you again. Okay. It's long, but not too hard. Okay. Okay, so let's move on. So the second definition I'm going to introduce is the dictating set. So a set X is called a dictating set if X can force A over B whenever A and B are two distinct candidates. So in other words, dictating sets can choose whoever they want. Sorry, there's an extra word. Right? So the dictating set says, you give me any two different candidates, I can force A over B. Right, for whoever it is. I can force him over the guy in the second row. I can force the guy in the second row also over him. So that's a dictating set. Is this okay? So X is a dictating set. If X has the power, he can do whatever he wants. He can put whoever above whoever, right? So that's really like a dictator. Right? The only thing is that X has many persons. Could be several people. Is it okay? So X is a dictating set, means he is powerful, right? Okay, so now let's make some observations. So if I take X to be the set of all voters, then X is a dictating set. Because if everybody in X places A above B, then by Pareto, B has no chance, so A would win, right? So if X is the set of all voters, of course, they can decide, right? Because collectively, all voters should have the power to choose whoever they want to choose, right? Is reasonable, right? So this is the biggest dictating set. Everybody, include everyone. Right? Now, what is the smallest dictating set? Dictator. So if P, if a single voter P, he is dictating, if P for some voter P is a dictating set, then this Mr. P is a dictator, right? Because his choice will determine the rest. If he puts A above B, A wins. If he puts B above A, B wins, right? So being a dictating set means only the people inside the set matters. The outside doesn't matter. So if inside the set only one person, that person is a dictator. Obvious, right? It's not hard, at least, right? Okay, so you are with me, right? Okay, so now what is the approach to prove Arrow's theorem? Arrow's theorem requires us to pick a dictator. So the goal is to show this paragraph. Okay, so question is, can you see why this is the case? Okay, so the rest of the argument is, I'm going to convince you this is true. If X is a dictating set, and if we split X into two sets, Y and Z, and then either Y is a dictating set or Z is a dictating set. So I have to explain what is splitting. So split means every element in X is in exactly one of the two sets, right? Y can be empty or Z can be empty, right? So for example, the split of people in this LT will, this is Y, these are Z, right? So everybody, including me, right? I'm on this side, so everybody is in one of the set. Okay, or I can split in other way. Maybe the first row and me are in Y, from second row onwards is in Z, right? So that's another split, okay? So the goal is to show, suppose X is dictating, and we split X into two parts, and then one of the parts is dictating. I claim that this is enough. Why? Because, right, you know, right? So if this is true, we can go from the biggest dictating set, everybody, just chop them into portions, right? One of the side is dictating, so you get a smaller guy dictating, and then chop it. One of the parts will be dictating. You get smaller size, and shrink. In the end, you get one, right? So this, okay, we need to assume the set of voters is finite. If it's infinite, then weird thing happens. But who is going to consider infinite many voters, right? So in real life, it's always finite. So you chop, and in the end, you get a dictating set with single element. That's the dictator, right? So the plan is clear, right? So by doing this, we go from the biggest dictating set to a smaller one, to the smallest one, right? Is it clear? So for example, suppose everybody here inside the LT is a dictating set, right? So I want to produce dictator. How I produce? I cut this, okay, I partition this, then one of the part is dictating. I don't know which one. Maybe, okay, for the sake of symphony. So maybe this side is dictating. So there are only 4 persons, right? These two guys. So these two guys are Y, and he and him are Z. Then one pair is dictating, right? So maybe these two guys are dictating. Oh, so only 2. Either you or you will be dictating. So one of them is dictator, right? So I'm going to do this. Okay, you are with me so far, right? Okay, good. That needs five lemmas to achieve this goal. Okay? So first one is the longest one, but it's not too long. Okay, so the first one says this. So suppose X forces A above B, and C is another candidate. Remember that in this argument, 3 or more voters is, 3 or more candidates is essential. So we need a third person to help us. So suppose X forces A over B, and C is another candidate. Now we split X into Y and Z. Okay? So then the claim is either Y forces A over C, or Z forces C over B. Well, what does it mean? So the intuition, the daily life explanation is this. So suppose X, right, this set has the power to force A high and B low, right? Force A over B, force A high and B low. And then either Y will inherit the power to force A high, right, compared to C. So either Y will force A high, A above C, or Z will inherit the power to force B low. So this probably help. So you have X, right? X can force A high, B low. Now cut X in half, then 1/2 will inherit some power. Either Y can force A high, or Z can force B low. Okay, so this is the claim. Okay. So the proof. Now we consider this situation. Okay. So let's consider this profile. I create a profile like this. Okay. So here the first column is the set Y. So everybody inside Y. The second column is everybody inside Z. And then everybody else was here. Okay? So I put the situation like this. Okay, ABC, CAB, BCA. So this is like the Condorcet example. So you have 2/3 of people prefer A over B, 2/3 of people prefer B over C, and 2/3 of people prefer C over A, something like this, right? So now I'm going to recycle this example. So look at this profile, okay? So now I copy the profile here so that we don't forget. Okay, so now since everybody in the first two columns, these so-called two-thirds people prefer prefer A above B. But Y union Z is X. X is dictating. So since everyone in the dictating set, which is in Y union Z, prefer A above B, so F will prefer A over B. Okay, so in this profile, F will produce A above B. Okay. Now, so the consequence is the F cannot put B over C at the same time C over A. Because if so, F will prefer B over C, and also the system will prefer C over A. It automatically prefer B over A. So because when we talk about the ballot, we see the preferred list has to be transitive. That's assumption. So F must produce a preferred list. So he has to produce a transitive thing. So in other words, F cannot do this. F cannot put B over C and C over A at the same time because F already put A over B, A above B. Okay? So now we learned De Morgan's law, right? The negation of an AND is a OR. So if F cannot put this and at the same time that, so either he fails this or he fails that. So either you put C above B, C over B, or put A over C. Here we use the decisiveness, so there's no tie. So it's either this or that. Okay, so we are here. So F will either put C over B or put A over C. Okay, right. So this is Then we are going to look at two cases. So what happens if F put C over B, and what happens if F put A over C? Okay, so again, I copy this table profile for your reference. So case one, F prefers A above C, right? So either, okay, so I'm considering put A above C, A over C. I consider the last part as my case one, this part as my case two. They are the same, actually. So suppose F prefers A over C. Then what? Now, then we have a set which is Y. So inside Y, every voter puts A above C, right? Everybody in Y put A above C, and everyone else, right, here put C above A. Okay. Then F goes with the set. F goes A over C. So by observation 1, remember that 5 minutes ago we looked at observation 1, which says it has A, B, 1, 2, 3. 1 says everybody inside the set prefer A over C. Number 2 says everybody outside the set do the opposite. Well, prefer C over A. And luckily F goes with the person in the set. Now, if we have this situation, the observation says actually Y forces A over C, right? So here actually we implicitly use this IIA and monotonicity. So we get Y force A over C, which is the Y will inherit the power to make A high. Okay? Now the other situation is the same. So suppose F goes that, then you'll see that inside Z, everybody prefer C over B. Everybody else prefer the other way. And F goes with Z. So Z will be the dictating set. Okay, so that's the end of lemma lemma 1. Okay, so we need to remember what it says. So let's, before we move on to the other lemmas, so it says this, right? Suppose x has power to force A high and B low. And then if you split x, either one part inherit power to force A high, or the other part inherit the power to force B low. Okay, so we are going to use that in 5 minutes' time. Okay, so we have seen this, Now, lemma 2. So suppose x forces A over B, and C is another candidate. And then x will force A over C, and x force C over B. Okay, so the intuition is, if x can force A over B, then x can force A over anyone. And also, x can force B under anybody. Read it one more time. Suppose x forces A over B. Now give me anybody, which is C. Right? X is going to force A above C. So actually x can do force A above anyone. And also x can force B below everyone. Right? So this is the lemma 2. We understand the statement, right? Okay? So the proof, so we use lemma 1. So we choose a special x and y. So we let y be the whole set x, and z be the set empty set. We don't give z a single person. Okay? So by lemma 1, either y force A high or y force B low. Right? So either y force A over C or z will force C over B. Okay? Now I want to convince you the empty set cannot force anything. This is as you expected. Right? So, but Z is empty set. He cannot force C over B. Why? Because otherwise, suppose empty set has this power. Right? From vacuum, you have this power. Now consider this ballot. Everyone put B over C. Right? Now, because F will still choose C over B. Why? Because the empty set choose C over B. I mean, you don't need anybody. Sorry. If Z forces, F will go with Z. Right? So Z would, F will go with Z, so F will choose C over B. Right? But everybody else, which is everybody in the world, will put B over C. Now, by Pareto, if everybody put B over C, C cannot be the winner. Right? So therefore, it can't be. So the empty set cannot force C over B. Otherwise, it's against Pareto. I guess this is probably quite obvious. So if it's empty set, it doesn't have power to to change the vote or whatever, right? Okay. So therefore, x equal y must force A over C, right? Because the second option doesn't exist. So y has to force A over C. And similarly, you can do the other way, then y will force C over B. Okay, so that's the lemma 2. Okay. Lemma 3 is easier. Lemma 3 says, if x force A over B, then x force B over A. So in other words, the forcing relation is symmetric. If x can force A over B, then I can force the other way. So x really have power. Okay. So the argument is quite easy. I use a diagram to show it. Okay, so if x can force A over B, as by lemma 2, x can force A above anybody. So in particular, x can force A above the third person C, right? So if x force A over C, x will force C below anybody. In particular, x will force C below B, right? Now, if X can force B above C, then X can force B above anybody. So X can force B above A, right? So from forcing A or B by using the third person, you can flip the order. You can get X force B or A, right? So this is easy. This is okay. Now, number 4. So suppose for some candidate A and B, X can force A or B, and then X is a dictating set. So as long as you force one pair, then you are dictating. So the intuition is if X has a little local power, right? Just force 2 guys, then X actually has complete global power, right? So if X can just force this pair, actually X can force anything he wants. Okay, so proof. Now let's show, right? How do I show X is dictating? Give me any 2. X can put whatever order they want, okay? So let's try. So give me C and D, any two person, right? 2 candidates. We want to show that X can force C over D, right? This is the meaning of dictating, okay? So there are 2 cases. So the case 1 is A is not D. Because in order to play the game, we need a different person. We cannot force A above A. So we have to use different person. So suppose A is not D. Now, if X can force A over B, X can force A above any person. No, I mean, not himself, but for example, X can force A over D. If X forces A over D, then X can force D below everybody, right? So in particular, X can force D below C, right? So X force C over D. Now the other case is similar. Suppose A happens to be D, and then if X force A over B, then by lemma 3, X will force B over A. So X can force A below anybody, so X will force A below C, but X is D, so X force C above D, right? So it is quite easy. So lemma 4 says, repeat, right? If X can just force one pair, then he is a dictator. Okay, last one. So this is really the goal. Okay, suppose X is a dictating set, and suppose we split X into Y and Z. Then either Y is dictating or Z is dictating. Okay, proof, easy. So, by the way, once we finish lemma 5, we achieve our goal, right? This is what we want to show. And that finished the proof of Arrow's theorem, right? Okay, so let's prove lemma 5. So let A, B, C be distinct candidates. Since X is dictating, X can force A over B, right? That's okay. Now bring in C. So by lemma 1, either X inherit the power to force A over C, or Z inherit power to force C over B. But by lemma 4, if you can force one pair, then you are dictating. So in other words, either Y is dictating because Y force A over C, right? Or Z is dictating. Z will force C over B. So one of the smaller set is dictating. Okay? So that is a proof. So it's not so bad, right? It's understandable. Whether it deserves Nobel Prize, I don't know, but this is we can follow. Okay, we can follow the logic. So the ending remark is back to the big question. So is there a voting system which is this, right? So which is anonymous, neutral, and decisive, and also Condorcet independent, IIA, Pareto, monotone. The answer is no, because by Arrow's theorem, the only possibility of satisfying 2 and 3, right? Decisive together with IIA, Pareto, and monotonicity will be dictator. But dictator violates number 1 because dictator is not anonymous. So it's an impossibility theorem. Okay, so that's the end of our topic on voting. So next week, I don't know, we probably talk about fire division or talk about graph. So I have to see which one is suitable. Okay, so see you next week.